You are sitting somewhere familiar, a room you trust, a chair that supports your weight, air that feels empty, passive, harmless. You do not question the space between objects. You do not question the silence inside the room. You assume that what is not filled with matter is simply nothing. That assumption feels safe, because if space itself were unstable, if emptiness were active rather than inert, then reality would not be resting quietly around you. It would be doing something, all the time. Modern physics tells you that the vacuum of space is not empty. That much is already accepted. But until recently, this idea remained abstract, something confined to equations, far removed from daily experience. Now that boundary is eroding. At the largest scientific instrument ever built, researchers are probing regions of space that should be calm, predictable, and mathematically well-behaved. Instead, they are finding behavior that should not exist. Fluctuations without cause, energy without source, effects that appear before their conditions are fully met. Nothing dramatic, nothing explosive, just small, precise deviations from how reality is supposed to work. And those deviations point toward a single, uncomfortable question. What if the vacuum is not the lowest possible state of reality? What if emptiness itself is unstable? And what if the universe you experience is balanced on something that should not exist at all? This is not science fiction. This is not metaphor. This is a real problem at the center of modern physics, and once you understand it, space will never feel empty again. You have always treated empty space as absence, a gap between objects, a passive stage on which reality unfolds. Nothing happens there unless something enters it. This intuition feels obvious because it works at human scales. You leave a room, and the room remains. You remove an object, and nothing replaces it. But physics does not describe space as absence. It describes it as a system, and systems do not remain perfectly quiet. At the scale of your body, emptiness behaves politely. It does not push back. It does not shimmer. It does not announce itself. Space appears to wait. That waiting feels neutral, almost comforting, because it suggests that reality is made of things, and that what is not a thing is irrelevant. This assumption quietly structures how you think about existence. Objects feel real because they occupy space. Events feel real because they happen in space. Space itself feels like a container, something that holds reality but does not participate in it. A background, a silence. Physics once agreed with you. In classical mechanics, space was exactly what it seemed to be, a static grid extending infinitely in all directions, nothing more than coordinates. Empty space had no properties of its own. It did nothing unless something moved through it. If all matter vanished, space would remain, unchanged and uneventful. That picture lasted because it was useful. It made prediction possible. It made the universe legible. But usefulness is not truth. When physicists began to probe smaller scales, scales far removed from rooms and chairs and air, the behavior of space stopped matching intuition. Emptiness began to misbehave. Measurements refused to settle. Systems that should have been silent exhibited motion, and the idea of nothing as a stable baseline quietly collapsed. At microscopic scales, space is not merely where things are. It is something that has to be described, constrained, and regulated. It possesses energy. It responds to conditions. It reacts to limits placed upon it. Remove all particles, all radiation, all matter, and something still remains. That something is not nothing. You can think of it this way. When you clear a table, the table remains. When you clear a room, the room remains. But when physics clears space of everything it can remove, the result is not empty in the way you expect. The equations still describe activity. They still predict consequences. They still produce measurable effects. This is not philosophical wordplay. It is experimental fact. The most unsettling part is how little effort it takes to demonstrate this. No exotic particles, no cosmic catastrophes, just carefully arranged boundaries, precise instruments, and patience. Even under the most controlled conditions imaginable, space refuses to behave like a blank slate. Your intuition fails because it evolved to survive at scales where these effects cancel out, where fluctuations average away, where instability hides beneath thresholds you never cross. At human scales, space appears calm because you are too large, too warm, too noisy to notice its restlessness. But calm is not the same as empty, and silence is not the same as absence. What physics reveals is not that space is filled with things, but that it is defined by processes. Continuous, unavoidable processes that do not switch off when matter leaves. You do not step into nothingness when you enter an empty room. You step into a region where countless interactions are happening below the resolution of your senses. That realization changes the role of space entirely. It is no longer a passive backdrop. It is an active participant, one whose behavior must be accounted for, whose limits must be respected, and whose stability cannot be assumed by default. Once you accept this, a deeper problem emerges. If space itself is a system, then it must have states. If it has states, it must have transitions. And if it can transition, then the version of space you experience may not be permanent. The comfort you feel in empty rooms depends on a silent assumption that nothing will continue behaving like nothing. Physics does not make that promise. In quantum field theory, empty space is defined as the lowest energy state of all fields combined, not zero activity, just the minimum allowed. That distinction matters, because even at its lowest energy, the vacuum fluctuates, fields briefly rise and fall. Particles appear and disappear too quickly to be directly observed. You are not surrounded by nothing. You are surrounded by instability held in check. The word vacuum suggests absence, a perfect clearing, a final removal of everything that could possibly act. But quantum theory does not permit such a state to exist. The laws themselves forbid complete stillness. What you call empty space is instead the most restrained version of activity reality can sustain. This is not because something is hidden there, waiting to be discovered. It is because the structure of the universe does not allow total silence. Every fundamental field, the electromagnetic field, the electron field, the Higgs field, exists everywhere, all the time. Even when no particles are present, the fields remain, and fields do not switch off. At their lowest energy, these fields continue to fluctuate, not in dramatic surges, not in ways that resemble motion in ordinary space, but in precise, quantifiable variations enforced by the mathematics of quantum mechanics. The vacuum is restless because it has to be. A perfectly calm state would violate the uncertainty principle, which places a hard limit on how precisely energy and time can be defined simultaneously. If a field's energy were exactly zero for an extended duration, the equations would break. So instead, the vacuum compromises. It allows small, transient deviations. Tiny surges of energy that rise and fall before they can stabilize into anything permanent. These fluctuations are not optional features of the theory. Remove them, and the theory stops working. Keep them, and emptiness becomes dynamic. This is where the idea of particles appearing and disappearing enters the picture. They are not objects popping into existence like sparks in the dark. They are brief excitations of fields, temporary rearrangements of energy that never fully detach from the vacuum. They cannot be directly observed because they are not independent entities. They are bookkeeping entries in the universe's balance sheet. And yet, their effects are real. They influence forces. They alter energy levels. They contribute measurable pressure. If you ignore them, predictions fail. If you include them, experiments align. This creates a quiet contradiction. The vacuum is defined as the absence of particles, yet particle-like effects emerge from it anyway. Not as violations of the rules, but as consequences of them. You are used to thinking of stability as stillness. A system at rest is one in which nothing changes. But quantum stability is different. It is not the elimination of change, but the confinement of it. The vacuum is stable not because nothing happens, but because what happens is constrained within narrow limits. That stability is not guaranteed by emptiness. It is enforced by balance, and balance implies tension. The unsettling implication is that the vacuum is not a neutral baseline. It is an active equilibrium, a state that persists because opposing tendencies cancel out. Fields fluctuate upward, but not too far. Energy appears, but not long enough to accumulate. The system survives by preventing any one deviation from dominating. This is why physicists sometimes describe the vacuum as seething. Not violently, not chaotically, but constantly, like a surface that appears smooth from a distance, but reveals endless motion when examined closely. You are immersed in this motion. Every moment of your existence is embedded in it. Your atoms, your thoughts, your sense of time all depend on fields whose lowest energy state is not nothing, but a controlled instability. And here is the deeper problem. If the vacuum is held together by balance rather than absence, then its persistence is conditional. It depends on the continued enforcement of constraints, on relationships between fields, on parameters that could, in principle, be different. The vacuum you inhabit is not the inevitable foundation of reality. It is one configuration among possible others, which means emptiness is not the end of the story. It is the beginning of a much more fragile one. These fluctuations are not optional features of reality. They are enforced by the uncertainty principle. You cannot know the energy of a system and the duration of that energy with perfect precision. The vacuum exploits this loophole constantly. For short intervals, energy appears from nowhere, and then it vanishes, or so it seems. The uncertainty principle is often described as a limitation on what you can measure. That framing is incomplete. It is not merely a problem of knowledge. It is a constraint on how reality itself is allowed to behave. Certain pairs of properties cannot be fixed simultaneously, not because instruments are flawed, but because the universe does not permit it. Energy and time are one such pair. If energy were locked perfectly at a specific value, time would lose definition. If time were fixed with absolute precision, energy would become indeterminate. The vacuum sits at the edge of this trade-off. It cannot remain perfectly still for any extended duration, because doing so would require infinite precision. So it fluctuates. These fluctuations manifest as what physicists call virtual particles. The name is misleading. They are not particles in the way you normally understand the term. They cannot be isolated. They cannot be captured. They cannot persist. They are temporary distortions in the fields that fill space, permitted by uncertainty and immediately corrected by it. They exist because the vacuum is not allowed to be exact. For a fleeting moment, a field's energy rises above its minimum. The equations tolerate this deviation as long as it disappears quickly enough. The shorter the interval, the larger the deviation can be. The longer it lasts, the smaller it must be. This is not an analogy. It is a quantitative rule, and the vacuum obeys it relentlessly. From your perspective, this looks like energy being borrowed and returned, a violation that repairs itself before it can be noticed. But nothing is actually borrowed. No rule is broken. The universe is simply operating within the margins it allows itself. What makes this unsettling is not that these fluctuations happen. It is that they happen everywhere, at every point in space, at all times. There is no empty region where this process stops. Even the most perfect vacuum ever produced in a laboratory still exhibits this behavior. Remove every atom, block every photon, cool the system toward absolute zero. The fluctuations remain. They are not caused by external disturbance. They are intrinsic, and although virtual particles cannot be observed directly, their consequences can. They modify forces between charged particles. They shift energy levels in atoms. They alter the propagation of light. Predictions that ignore them fail. Predictions that include them succeed with disturbing precision. This forces a quiet revision of how causality is understood. If effects emerge from fluctuations that have no single cause, then not every event traces back to a prior, identifiable trigger. Some outcomes arise from the structure of possibility itself, from what the universe permits rather than from what it intends. You may be tempted to dismiss this as mathematical abstraction, but the vacuum does not care whether you find it intuitive. Its behavior has been tested repeatedly across decades in experiments that depend on its predictions being correct. And they are. The price of uncertainty is that the vacuum is never fully settled. It is always negotiating the boundary between what is allowed and what is forbidden. Virtual particles are the visible trace of that negotiation. This has an important implication. If the vacuum is constantly fluctuating, then it is constantly sampling nearby states. Most of these deviations are small, harmless, immediately erased. But the system does not know in advance which fluctuations will occur. It only enforces limits after the fact. That means the vacuum is not passively stable. It is actively restrained. Stability in this context is not the absence of deviation. It is the suppression of escalation, and suppression implies the possibility of failure. If the rules that govern these fluctuations were slightly different, or if the energy landscape of the vacuum were shaped another way, then a fluctuation might not vanish. It might persist. It might grow. It might push the system into a new configuration entirely. For now, that does not happen. But the reason it does not happen is not because emptiness is inert. It is because uncertainty is being constantly paid for, moment by moment, everywhere you exist. For decades, vacuum fluctuations were treated as mathematical artifacts, useful, but not directly real. Then experiments like the Casimir effect showed otherwise. Two uncharged metal plates placed close together experience a measurable force, caused entirely by changes in the vacuum between them. Empty space pushed back. At first, this result seemed almost embarrassing. The equations predicted it, but no one expected it to matter outside of calculations. The vacuum was allowed to fluctuate on paper because the mathematics demanded it, not because anyone believed those fluctuations could ever leave a physical trace. They were tolerated as internal bookkeeping, necessary to make predictions come out right. but not something you would ever feel. The Casimir effect changed that assumption quietly and decisively. When two conductive plates are placed extremely close together in a vacuum, something subtle happens. The spectrum of allowed vacuum fluctuations between the plates becomes restricted. Certain wavelengths no longer fit. Outside the plates, the vacuum continues fluctuating freely. Inside, it does not. This imbalance creates pressure, not from particles, not from radiation, but from the structure of the vacuum itself. The plates are pushed together because the vacuum outside them exerts more influence than the vacuum trapped between them. The force is small, but it is real. It can be measured. It can be predicted. It can be repeated. And it cannot be explained without accepting that empty space has physical consequences. This was not a new force being discovered. It was an old assumption being exposed, the assumption that emptiness does nothing. The Casimir effect does not rely on exotic conditions. It does not require extreme temperatures or cosmic energies. It occurs in laboratory-scale experiments using ordinary materials. The only requirement is precision, bringing objects close enough that the vacuum's internal structure can no longer hide. Once measured, the vacuum could no longer be dismissed as a mathematical convenience. It had become an experimental participant. This creates an uncomfortable shift in perspective. If the vacuum can push, then it has pressure. If it has pressure, then it has energy. If it has energy, then it contributes to the dynamics of the universe. Empty space is no longer empty in any operational sense. It affects outcomes. It changes forces. It alters what happens when objects approach one another. It is not a backdrop. It is part of the interaction. You might be tempted to minimize this by scale. The Casimir force is tiny. It does not move planets. It does not shape galaxies. It does not disrupt daily life. But scale does not determine significance. Structure does. The same vacuum that produces this force exists everywhere. The same principles apply at every point in space. The only reason you do not notice them constantly is because they usually cancel out. Symmetry hides their influence. Balance keeps their effects small. But the moment symmetry is broken, even slightly, the vacuum responds. This matters because it tells you something fundamental about reality. The vacuum is sensitive to boundaries. It reacts to constraints. It does not behave the same way in all circumstances. Its properties depend on context. That is not how nothing is supposed to behave. In classical thinking, removing all matter removes all influence. In quantum reality, removing matter reveals something else entirely, a background that was always active but rarely exposed. The Casimir effect is not disturbing because it introduces a strange force. It is disturbing because it confirms that the vacuum has rules, and those rules can be manipulated. By arranging objects in certain ways, you change how empty space behaves. This means the vacuum is not an immutable foundation. It is responsive. And responsiveness implies fragility. If the vacuum's behavior can be altered by the presence of two metal plates separated by micrometers, then it is not difficult to imagine circumstances, energetic, cosmic, or extreme, where its structure could be altered more dramatically. The Casimir effect does not threaten reality, but it removes a layer of comfort. It proves that fluctuations are not confined to theory, that the vacuum's instability is not merely conceptual, that under the right conditions, emptiness announces itself, and once emptiness can push back, the question is no longer whether the vacuum is real. The question becomes how much pressure it is already exerting, everywhere you are not looking. Once measured, the vacuum stopped being theoretical. It gained properties: pressure, energy density, directional behavior. The question shifted from, does the vacuum do anything, to what exactly is it doing all the time, and whether it is doing too much. The moment the vacuum produced measurable effects, it crossed an important boundary. It could no longer be treated as a convenient abstraction. It had entered the category of things that act, and once something acts, it must be described, quantified, constrained. This is where the idea of structure becomes unavoidable. Structure does not mean solidity. It does not mean shape in the everyday sense. It means internal organization, rules governing behavior, relationships that persist even when nothing visible is present. The vacuum exhibits all of these. It has energy density, meaning that each region of space contains a definable amount of energy even when no particles are present. That energy can change under certain conditions. It can be redistributed. It can contribute to forces. This alone would have been unthinkable in classical physics. It also has pressure. Not metaphorical pressure, but real pressure, capable of influencing matter. The Casimir effect revealed this locally, but the implication extends much further. Pressure implies resistance. It implies response. It implies that space does not merely allow events to happen within it, but participates in determining how they unfold. Even more unsettling is the realization that the vacuum is not perfectly uniform in all circumstances. Under strong fields, extreme energies, or particular boundary conditions, its behavior changes. Directions that were once equivalent cease to be so. Symmetry breaks. Preferred orientations emerge. This is not how emptiness is supposed to behave. If space were truly nothing, it would not matter how you probed it. Every direction would be the same. Every point would be equivalent. There would be no internal features to distort. But experiments and theory agree on this point. The vacuum responds differently depending on how it is constrained. Its properties are context-dependent. That dependence suggests that the vacuum is not a single, featureless state. It is a configuration, one among many possible configurations allowed by the underlying laws. The one you inhabit is defined by specific values: field strengths, coupling constants, energy minima, that do not have to be what they are. This realization forces a conceptual shift. Instead of thinking of particles as objects moving through empty space, you must think of them as excitations of fields embedded within a structured vacuum. Matter becomes secondary. The vacuum becomes primary. What you perceive as solidity is a localized disturbance riding on top of a deeper system. Your existence, then, depends less on the presence of matter and more on the stability of the vacuum's structure. The fields must remain in the configuration they currently occupy. The energy landscape must retain its shape. The balance that suppresses runaway fluctuations must hold. If that balance were to change, the vacuum would not merely behave differently. It would redefine what behavior is possible at all. This is where the question of doing too much emerges. A system with structure can evolve. It can transition. It can move from one configuration to another if conditions allow. The vacuum is no exception. Its structure implies multiple possible states, separated by energy barriers. As long as those barriers hold, the vacuum remains as it is. But barriers are not absolutes. They are probabilistic constraints. The vacuum you experience may be stable, or it may be metastable, stable enough to persist for long periods, but not guaranteed forever. The difference matters, because a metastable system does not fail gradually. It persists, and then it changes abruptly. The troubling part is that nothing in your daily experience tests this stability. The vacuum does not announce its condition. It behaves consistently across all scales you can observe directly. Its structure supports atoms, chemistry, biology, and thought without visible strain. But consistency is not proof of permanence. The discovery that the vacuum has structure replaces a comforting assumption with a fragile one. You no longer live in a universe where nothingness forms an immutable foundation. You live in one where the foundation itself has properties that must be maintained. The question is no longer whether the vacuum is real. It is whether its current structure is as inevitable as it feels, and whether the silence of empty space reflects stability or restraint. At CERN, precision matters more than scale. The Large Hadron Collider is not just a particle smasher. It is an instrument for interrogating the vacuum itself. Particles are accelerated through near-perfect emptiness. Fields are isolated. Noise is eliminated. What remains should be predictable. It isn't. The popular image of the Large Hadron Collider is violent. Particles colliding, energies exploding, debris flying outward. That image misses the deeper purpose. Before anything can collide, the environment must be controlled to an extreme degree. The beams travel through an engineered vacuum more perfect than any natural void. Stray particles are removed. Thermal motion is suppressed. Electromagnetic interference is corrected for. Every known source of disturbance is accounted for. This level of control is not aesthetic. It is necessary. When you push particles to near the speed of light, even the smallest irregularity matters. A single unexpected interaction can ruin an experiment. Precision is not optional. It is the entire point. And yet, even under these conditions, the results are not fully obedient. When particles move through this controlled emptiness, their behavior reflects not only their own properties, but the properties of the space they traverse. Their masses shift slightly. Their interactions differ subtly from what simpler models predict. Probabilities skew. Outcomes cluster in ways that suggest an influence that cannot be attributed to the particles alone. What remains, after everything removable has been removed, is the vacuum. The LHC does not merely test particles against one another. It tests how particles exist within space. It probes the vacuum at energy scales never before accessible. And as those scales increase, the vacuum responds in ways that feel less like a passive medium and more like a system under strain. The expectation was not that everything would be simple. Physics has long accepted complexity at high energies, but there was an assumption beneath that acceptance that the vacuum itself would remain well-behaved, that its role would be consistent, if not trivial. Instead, precision experiments reveal that the vacuum's contribution changes with energy. Parameters that should remain constant appear to run. Interactions that should scale smoothly begin to drift. The equations still work, but only after careful adjustment. Only after acknowledging that the background is not fixed. This does not mean the experiments are failing. It means they are succeeding too well. The more precisely the vacuum is isolated, the more clearly its influence appears. Noise has been eliminated, and what remains is not silence, but structure. Subtle, persistent, unavoidable. From a theoretical standpoint, this is expected. Quantum field theory predicts that the vacuum's properties depend on the energy scale at which it is examined. Fields interact with their own fluctuations. Contributions accumulate. Effective values shift. None of this violates known laws. What is unsettling is how central this makes the vacuum. At CERN's energies, you are no longer just smashing particles together. You are deforming the energy landscape of empty space itself. You are forcing the vacuum into regimes it does not encounter naturally, and when you do, it answers, not loudly, not catastrophically, but precisely. The answers are numbers that do not quite settle, curves that bend when they should flatten, dependencies that reveal hidden depth. Each deviation is small, each one can be explained, but together they form a pattern that undermines a comforting assumption that emptiness is simple. The LHC was designed to discover particles like the Higgs boson. It succeeded, but in doing so, it also confirmed something more disturbing: that the vacuum is not a fixed stage on which particles perform. It is part of the performance. Its properties are entangled with the phenomena it hosts. This means that when physicists speak about fundamental constants, they are often speaking about vacuum properties. When they discuss stability, they are discussing the stability of space itself, and when they test the limits of known physics, they are testing how much the vacuum can be pushed before its behavior qualitatively changes. What remains unpredictable is not the outcome of any single collision. It is the deeper question of whether the vacuum being interrogated is the most stable configuration possible, or merely the one that happens to exist at this moment. At CERN, absence is no longer assumed to be empty. It is measured, and the measurements suggest that emptiness has more to say than expected. Some measurements at high energies show slight inconsistencies, not errors, not noise, patterns. The vacuum behaves differently depending on energy scale, as if its structure changes when pushed too hard, as if emptiness has phases. At first, these deviations were easy to dismiss. They were small, fractions of a percent, tiny shifts buried deep in statistical margins. Nothing that screamed anomaly, nothing that demanded headlines. Physics is full of such imperfections, and most of them dissolve with better data, improved calibration, or longer observation. But these did not dissolve. They persisted across experiments, across detectors, across methods. The numbers moved, but not randomly. They bent in the same direction. They clustered. They obeyed relationships that suggested underlying order rather than mistake. This is where discomfort enters. Physics is built to tolerate noise. It is not built to tolerate consistent deviation without explanation. When measurements repeat the same small disagreement with expectation, the problem is not precision. The problem is assumption. The assumption under strain is subtle but foundational, that the vacuum behaves the same way at all energy scales, that emptiness is scale invariant, that probing it harder reveals more detail, not different rules. The data challenges this. As energies increase, the effective properties of the vacuum shift. Coupling strengths change. Interaction probabilities evolve. The background against which particles exist appears to reorganize itself, not abruptly, not violently, but measurably. This behavior is familiar in other systems. Water behaves one way as ice, another as liquid, another as vapor. The molecules are the same. The structure is not. Phase transitions alter what interactions are possible without changing the underlying components. The unsettling implication is that the vacuum may behave similarly. At low energies, it appears stable, uniform, predictable. At higher energies, it reveals internal degrees of freedom. Constraints loosen. Contributions emerge that were previously suppressed. The same vacuum expresses different effective behavior depending on how deeply it is interrogated. This does not violate quantum field theory. In fact, the mathematics anticipates it. Parameters run with energy. Renormalization accounts for shifting contributions from fluctuations at different scales. Everything remains internally consistent. But consistency is not comfort, because what this means is that the vacuum you experience is not a single, absolute state. It is a low-energy approximation of something more complex, a calm surface over deeper structure. When experiments reach higher energies, they are not merely examining particles more closely. They are accessing layers of the vacuum that are normally irrelevant to everyday reality. Layers where the balance that defines stability looks different. The deviations are small because the energy scales required to fully expose these effects are immense. But small does not mean insignificant. In physics, tiny deviations often point toward profound revisions. They are the first visible cracks in assumptions that hold only under limited conditions. What makes this particularly unsettling is that there is no clear boundary where behavior changes, no sharp threshold, no single energy at which the vacuum announces a new phase. Instead, the transition appears gradual, smooth, continuous. This suggests that the vacuum is not protected by an absolute barrier. It is regulated by relationships that can shift continuously as conditions change. Push hard enough, and the rules deform. The phrase "emptiness has phases" is not poetic exaggeration. It is a serious theoretical possibility. Different vacuum states, characterized by different field configurations, different symmetries, different energy minima. The one you inhabit may simply be the phase that emerges at low energies, and phases can change, not because something external intervenes, but because internal conditions evolve, because fluctuations sample regions of possibility that are normally suppressed, because stability is maintained statistically, not guaranteed absolutely. The deviations observed are not warnings. They are not signals of imminent transition. They are reminders that the vacuum is not inert, that its apparent simplicity is contingent, that its behavior depends on how hard it is pushed. You are accustomed to thinking that laws of physics are fixed and that energy merely reveals them. These measurements suggest something subtler, that at higher energies, you are not just revealing deeper laws, you are changing the effective environment in which those laws operate. The vacuum does not merely host reality, it participates in determining which version of reality is allowed to exist. Physics allows for the possibility that the vacuum you inhabit is not the true lowest energy state of reality. It may be metastable, stable enough to persist, unstable enough to eventually fail, like a ball resting in a shallow valley instead of the deepest one. This idea feels abstract until you consider what stability actually means in physics. Stability is not permanence. It is resistance to change under small disturbances. A system can appear perfectly calm while still being vulnerable to a larger rearrangement. The ball does not roll because nothing has pushed it far enough, not because there is nowhere lower to go. In quantum field theory, the vacuum is defined by the configuration of fields that minimizes energy. But minimization does not guarantee absoluteness. Complex systems often have multiple minima, local low points separated by barriers. The system settles into one because it is nearby, not because it is the deepest possible. The false vacuum hypothesis proposes that the universe occupies such a local minimum, a configuration that is internally consistent, long-lived and stable under ordinary fluctuations, but not the true ground state, not the lowest energy arrangement allowed by the laws themselves. This is not an exotic proposal. It emerges naturally from the mathematics of fields interacting with one another. When multiple fields coexist, their combined energy landscape becomes intricate. Valleys form within valleys. Barriers arise that prevent easy transition. The universe chooses a state not by preference, but by accessibility. If this is correct, then the vacuum you experience is not inevitable. It is historical, a consequence of how the early universe cooled, expanded, and settled. Different initial conditions could have led to a different vacuum, one with different properties, different constants, different rules. This reframes existence in a subtle way. The laws of physics you rely on may not be fundamental truths. They may be emergent features of the vacuum's current configuration. Change the vacuum, and the laws change with it. The unsettling part is not that a lower energy state exists. It is that nothing requires the universe to stay where it is forever. Metastability means persistence without guarantee. A state can last longer than the current age of the universe and still be temporary in principle. Quantum mechanics allows for transitions that do not require an external push. Even if the ball sits quietly, there is a non-zero probability that it will tunnel through the barrier separating it from the deeper valley. No warning, no gradual descent. One configuration, and then another. If such a transition were to occur, it would not resemble destruction. There would be no explosion in the conventional sense. Instead, the underlying structure of space would change. Fields would rearrange into a new minimum. Particle properties would be redefined. Forces would take on new relationships. Everything dependent on the old vacuum would cease to function as before. This possibility is deeply unsettling because it is invisible from within. The false vacuum does not advertise its status. It behaves exactly like a true vacuum as long as it remains intact. All experiments conducted within it reinforce its consistency. There is no internal test that can definitively confirm whether it is the lowest state or merely a stable one. The difference exists only in the global structure of the energy landscape, something you cannot fully map from a single valley. This means that certainty about ultimate stability is not achievable through observation alone. It is inferred from theory, constrained by measurement, but never proven absolutely. The false vacuum hypothesis does not predict imminent catastrophe. The probabilities involved are extraordinarily small. The timescales may dwarf cosmic history, but probability is not zero, and in physics, non-zero matters. More importantly, the hypothesis undermines a comforting assumption that the universe exists because it must. Instead, it suggests that the universe exists because it has not yet changed state. Your reality, then, is not anchored by necessity. It is anchored by delay. The vacuum beneath everything you experience may be a temporary solution to a deeper equation, one that works remarkably well, one that has lasted long enough for galaxies, stars, and thought to emerge, but one that is not guaranteed to last forever. And once you accept that, stability stops being a background condition. It becomes the central question. A false vacuum does not decay gradually. It fails suddenly. A transition would propagate at the speed of light, rewriting physical laws as it expands. No warning, no observable precursor. Reality would simply change. This is the feature that separates false vacuum decay from every failure mode you intuitively understand. There is no fatigue, no accumulation of damage, no measurable weakening. The vacuum does not fray at the edges. It does not signal distress. It remains internally consistent until the moment it does not. In ordinary systems, stability is monitored by feedback. You can observe strain, detect imbalance, measure drift. A bridge vibrates before it collapses. A star brightens before it explodes. Even radioactive decay can be tracked statistically, but the vacuum offers no such markers. Its decay is not a process unfolding in time. It is a transition between states. In quantum field theory, this transition occurs through tunneling. The vacuum does not need to climb over an energy barrier. It passes through it. One moment the fields occupy a metastable configuration. The next, a region of space finds itself in a lower energy state. That region is not a disturbance within the old vacuum. It is a replacement. Once formed, this new vacuum state expands outward at the maximum speed allowed by the universe. Not because it is driven, but because nothing can resist it. The laws governing the old vacuum simply do not apply inside the new one. There is no interface where compromise occurs. The boundary is absolute. As it expands, it does not destroy matter in the conventional sense. Matter ceases to be defined. The particles you rely on, electrons, quarks, photons, are excitations of fields configured for the old vacuum. When the vacuum changes, those excitations are no longer valid solutions. Chemistry does not fail. It becomes meaningless. There is no pain, no awareness, no final moment. The transition arrives already complete. What makes this particularly unsettling is that the decay does not require a cause in the usual sense. It does not need a collision, a perturbation, or an external trigger. The probability is intrinsic. As long as the vacuum is metastable, the possibility exists. The system does not need to be pushed. It only needs to exist long enough. From within the vacuum, there is no experiment you can perform that guarantees safety. You can constrain parameters. You can refine measurements. You can test consistency. All of these confirm that the vacuum is stable under small disturbances. None of them rule out tunneling. This is not because physics is incomplete. It is because the concept of absolute stability is stronger than what physics can offer. Stability, in this context, is statistical. It is a statement about likelihood over time, not certainty. A decay with an expected lifetime, vastly exceeding the age of the universe, is still a decay. It is merely delayed. This reframes how you think about permanence. The laws of physics feel immutable because they have held without exception throughout recorded observation. But that record spans an insignificant fraction of cosmic time. The vacuum's persistence so far does not imply inevitability. It implies survival. And survival is not proof. The uncomfortable truth is that if false vacuum decay were to occur, it would not register as an event within the universe. It would be a change of the universe. There would be no before and after from the inside, only a before. This is why the possibility cannot be dismissed emotionally or intuitively. It is not dramatic. It is not catastrophic in the narrative sense. It is quiet, final, and unobservable. The reason stability is not guaranteed forever is not because the vacuum is poorly constructed. It is because the laws that allow it also allow something else, a lower energy configuration that does not announce itself in advance. Your universe may be balanced in a way that feels permanent because balance has held for billions of years. But physics does not equate duration with necessity. It equates it with probability. And probability, no matter how small, is not zero. You cannot detect a lower vacuum state from within the higher one. The mathematics forbids advance notice. The decay would arrive already complete. The universe would not explode. It would be replaced. This limitation is not technological. It is not a matter of insufficient instruments or incomplete data. It is structural. The equations that describe vacuum decay do not contain any observable precursor that exists within the metastable state itself. From the inside, the false vacuum is self-consistent. Every measurement you can perform confirms its rules, reinforces its stability, and validates its internal logic. The deeper vacuum does not cast a shadow backward into the one you inhabit. To understand why, you have to abandon the idea that the vacuum is an object embedded in space. It is the definition of space. A lower vacuum state is not somewhere else, waiting to be discovered. It is not adjacent. It is not hidden behind a boundary you might cross with enough energy or precision. It is a different configuration of reality. As long as you remain within the higher energy vacuum, all physical processes are governed by its fields, its constants, its symmetries. Any probe you construct is made of excitations of those fields. Any detector you design relies on interactions that only exist because the vacuum has the structure it does. You cannot step outside the vacuum to examine alternatives. There is no external reference frame. This is why advanced detection is impossible in principle. The decay does not announce itself because it is not an event occurring within the vacuum. It is the vacuum ceasing to be the relevant description. There is no gradual approach, no softening of parameters, no instability that grows louder with time. The probability exists, but probability is not a signal. When the transition occurs, it begins as a region, infinitesimal at first, where the fields settle into a lower energy configuration. That region is not unstable. It is more stable than the surrounding space. It expands not because it is pushed, but because the old vacuum cannot persist in its presence. The expansion proceeds at the speed of light because nothing can outrun the redefinition of physical law. There is no friction between vacuum states. There is no medium to slow the transition. The boundary marks where one set of rules ends and another begins. From your perspective, there is no experience of crossing that boundary. You do not observe the wavefront approaching. You do not register a change in constants. You do not feel forces shifting. Every mechanism that could register such changes depends on the old vacuum structure, and that structure vanishes at the boundary. The universe does not explode because explosions require time, energy transfer, and observers embedded in a stable framework. None of those survive the transition. Replacement is quieter. The idea of replacement is difficult to grasp because it lacks drama. It does not resemble any failure mode you are familiar with. There is no collapse, no expansion of debris, no aftermath. The old universe is not damaged. It is invalidated. This is why false vacuum decay cannot be treated as a conventional risk. It does not fit into categories of danger, catastrophe, or destruction. Those are events that occur within a universe. This is a change of universe. The impossibility of advance notice is not a gap in knowledge that might be closed with better theory. It is a consequence of consistency. If the false vacuum could detect its own instability through internal measurement, it would not be metastable in the first place. The very definition of metastability requires that the state appear fully stable under all internal tests. This creates a peculiar asymmetry. From the outside, if such a perspective were possible, the decay would be obvious. One vacuum state gives way to another. Energy decreases. Stability increases. From the inside, there is no story to tell, only a continuation that ends without transition. This is why physics treats the possibility with such restraint. There is nothing to prepare for, nothing to observe, nothing to respond to. The theory predicts the possibility, not the experience. The most unsettling implication is not that the universe could end this way. It is that, if it did, there would be no moment in which you were wrong about reality. right up until the moment reality stopped being what it was. The measured mass of the Higgs boson places the universe disturbingly close to theoretical instability. Not clearly stable, not clearly doomed, balanced. This is not comforting. When the Higgs boson was discovered, it was celebrated as a triumph of prediction, a missing piece finally confirmed. The mechanism that gives particles mass validated by experiment. For a moment, the universe felt complete in a way it rarely does. Then the number was measured. The Higgs boson's mass was not arbitrary. It landed in a narrow range that carries consequences far beyond particle physics. That value determines the shape of the Higgs field's energy landscape. And the shape of that landscape determines whether the vacuum defined by the Higgs field is absolutely stable, metastable, or unstable. The result was not reassuring. If the Higgs were slightly lighter, calculations suggest the vacuum would be safely stable. If it were slightly heavier, instability would be unavoidable. Instead, the measured value sits near the boundary between the two, close enough that small changes in other parameters, top quark mass, coupling strengths, high energy corrections, can tip the conclusion either way. This is not a clean result. It is a knife edge. The Higgs field permeates all of space. Its non-zero value defines what mass means. Electrons, quarks, atoms, none of them behave as they do without it. The vacuum you experience is inseparable from the Higgs field's configuration. If that configuration is only metastable, then the foundation of mass itself is provisional. The unsettling part is not that the calculations are uncertain. Physics often lives with uncertainty. The unsettling part is that even with current uncertainties accounted for, the universe does not land comfortably in the stable region. It hovers near instability without obvious reason. Balanced systems invite questions. In nature, balance is usually enforced. A marble balanced at the bottom of a bowl is stable because the shape demands it. A marble balanced on a ridge requires explanation. Why is it there? What holds it in place? How long can it remain? The Higgs field appears to be balanced in this second sense. From a purely mathematical perspective, this could be coincidence. The parameters of the universe take the values they take. No further explanation required. But physics has learned to be suspicious of coincidences that affect everything, because this balance is not local, it is global. The Higgs field's value is uniform across the observable universe. Its mass influences vacuum stability everywhere at once. A coincidence on this scale feels less like chance and more like constraint. Some theories attempt to explain this balance through deeper principles. New physics at higher energies, hidden symmetries, additional fields that stabilize the Higgs potential before it can turn unstable. None of these have been confirmed. For now, the simplest reading remains. The universe is close to metastable. Close does not mean fragile in human terms. The expected lifetime of such a vacuum can exceed the age of the universe by many orders of magnitude. But lifetime is not the same as inevitability. A system can be long-lived and still temporary. The discomfort comes from the absence of necessity. Nothing in current theory demands that the Higgs mass sit where it does. Nothing enforces its proximity to instability. The equations allow wide ranges of values that would produce universes very different from this one. The fact that this universe lands where it does is not explained by the model that describes it. This places you in an unusual position. You live in a universe whose most fundamental field appears tuned to a threshold. Not catastrophically unstable, not robustly safe. Balanced in a way that permits existence without guaranteeing it. This balance does not announce danger. It does not predict collapse, but it undermines the idea that stability is fundamental. The Higgs field does its job flawlessly. It gives mass. It enables structure. It supports everything you experience. And in doing so, it quietly encodes the possibility that this support is conditional. The awkward number is not alarming because it predicts failure. It is alarming because it refuses to explain why failure is avoided. And in physics, unexplained balance is not reassurance. It is an invitation to look deeper and to accept that what you stand on may be less solid than it appears. Physical systems rarely remain balanced indefinitely without enforcement. If nothing stabilizes the vacuum, its persistence becomes a coincidence. And coincidences are not explanations. Balance often feels reassuring because it looks like control. A system that does not drift, does not collapse, does not visibly change, gives the impression of security. But in physics, balance is ambiguous. It can mean stability or it can mean suspension. A system at true equilibrium resists disturbance. Push it slightly, and it returns to its original state. A system in mere balance does something else. It tolerates stillness, but it does not correct deviation. The difference is subtle, and it matters. The vacuum appears balanced. Its parameters remain constant across vast stretches of space and time. The fields that define it maintain their values. The laws that emerge from it remain consistent. Nothing obvious pushes it toward change, but consistency alone does not reveal why this balance holds. In well-understood systems, balance is enforced by structure. A planet remains in orbit because gravity and motion constrain it. An atom remains intact because electromagnetic forces bind it. In both cases, if a disturbance occurs, the system responds predictably. Stability is built in. The vacuum offers no such visible enforcement. Its apparent balance emerges from the interplay of fields whose parameters are set by values we do not derive from deeper necessity. The Higgs field sits near a threshold. Couplings run with energy. Corrections from higher scales could reshape the energy landscape entirely. And yet, the vacuum persists. The question is not whether it persists. The question is why. If nothing actively stabilizes the vacuum, no symmetry, no principle, no deeper constraint, then its persistence is not guaranteed. It is contingent. A result of initial conditions and probability rather than necessity. This is where coincidence becomes uncomfortable. Physics accepts coincidence reluctantly. It tolerates it temporarily. But when coincidences stack, when multiple parameters align just enough to permit existence, structure, and stability, explanation is demanded. Either something deeper enforces the alignment, or the alignment is accidental. The vacuum's balance sits in this unresolved space. Some theories propose hidden stabilizers. Supersymmetry could flatten the Higgs potential. New particles at higher energies could reshape the vacuum landscape. Unknown dynamics could lock the system into a safe configuration. These ideas are mathematically consistent. None have been observed. Until such enforcement is found, balance remains unexplained. This does not mean the vacuum is unsafe. It means safety has not been demonstrated. There is a difference. A bridge that has not collapsed may still lack structural redundancy. Its survival so far does not prove its design is sound. It proves only that stress has not exceeded tolerance. The vacuum has survived cosmic inflation, galaxy formation, stellar collapse, and particle collisions at energies far beyond everyday experience. That endurance is impressive, but endurance is historical, not fundamental. It tells you what has happened, not what must happen. The danger of confusing balance with safety is conceptual. It leads you to treat persistence as proof. It encourages the belief that because something has lasted, it will continue to last. Physics does not endorse this logic. In fact, physics often teaches the opposite. Many systems remain stable for long periods before transitioning abruptly. Metastable states can dominate behavior for durations that dwarf observation. Their eventual decay does not require warning signs. It requires only time. If the vacuum is such a state, then its balance is not protective. It is deceptive. The unsettling implication is that the universe may not be held together by necessity, but by circumstance. That what feels fundamental is simply what has not yet changed. That stability is not an intrinsic property of reality, but a temporary outcome of how its components currently align. This does not diminish the reality you experience. It explains it in a different way. Your universe may exist not because it must, but because it can, and because, so far, it has not found a reason to do otherwise. Balance, in this context, is not a guarantee. It is a condition. And conditions, unlike laws, can change. At extreme energies, known laws begin to lose consistency. Renormalization fails. Predictions diverge. The vacuum stops behaving like a background and starts behaving like an active participant. The laws of physics come with an implicit promise that if you understand them well enough, you can apply them anywhere, at any scale, and they will continue to hold. This promise works remarkably well across most of what you experience. From falling objects to atomic spectra, from electronics to stars, the same frameworks apply with only minor adjustments. But this promise has limits. As energy increases, the mathematics that once felt solid begins to strain. Quantities that were well-behaved become sensitive. Corrections grow instead of shrinking. Calculations that once converged begin to diverge. The tools that made sense of the world stop delivering clear answers. This breakdown is not sudden. It is gradual and technical, easy to miss unless you are looking for it. Renormalization, the method used to absorb infinities and extract meaningful predictions, works because the vacuum behaves predictably at lower energies. Fluctuations can be accounted for. Contributions can be organized. Effects from inaccessible scales can be summarized cleanly. At extreme energies, that separation fails. Contributions from the vacuum no longer remain small corrections. They begin to dominate. Fluctuations at different scales interact in ways that resist simplification. Parameters that were once stable begin to run uncontrollably. The distinction between particle and background blurs. This is not because the theory is wrong in the usual sense. It is because the assumptions that make it usable stop being valid. At low energies, you can treat the vacuum as a fixed stage. Particles move through it. Forces act within it. Its role is indirect. At high energies, this approximation collapses. The vacuum's structure becomes inseparable from the phenomena unfolding within it. You are no longer studying particles in space. You are studying space under stress. The vacuum begins to respond to energy input in ways that resemble material behavior. Its properties shift. Its effective constants change. Symmetries that held at lower energies can break or deform. The system reveals that what you thought were fundamental laws were contingent on the vacuum remaining calm. This is deeply unsettling because it undermines a common intuition that laws of physics are external rules imposed on reality. At extreme energies, they look more like emergent behaviors, rules that hold only as long as the vacuum remains in a particular configuration. When renormalization fails, it is not merely a mathematical inconvenience. It is a signal. It tells you that your description has reached the boundary of its validity. that you are probing regimes where the vacuum can no longer be ignored or averaged away. In these regimes, predictions depend sensitively on details you cannot fully control. Unknown physics at higher scales intrudes. The vacuum becomes an active participant, shaping outcomes rather than quietly enabling them. This matters because the vacuum is not optional. You cannot remove it to simplify the problem. It is the medium in which all interactions occur. When its behavior changes, everything changes with it. The discomfort comes from the realization that physics does not promise consistency at all scales. It promises consistency only within domains where its assumptions hold. Beyond those domains, it offers hints, not guarantees. The vacuum's increasing influence at high energies suggests that stability is scale-dependent. What looks safe and well-defined at one scale may be precarious at another. The laws you trust may be effective descriptions, not absolute truths. This does not mean physics fails entirely at extreme energies. It means that what you call physics becomes incomplete. It gestures toward deeper structures it cannot fully describe. And those deeper structures appear to be vacuum-dependent. If the vacuum's properties determine which laws apply, then probing higher energies is not merely an act of discovery. It is an act of interrogation. You are asking the vacuum how it behaves when pushed beyond its comfort zone. The answers are not reassuring. They suggest that emptiness is not infinitely accommodating, that it has regimes where its internal structure asserts itself forcefully, that beyond certain thresholds, the universe no longer behaves like a collection of objects obeying fixed rules, but like a system whose foundational assumptions are being renegotiated. At these energy scales, physics does not break because reality becomes chaotic. It breaks because reality becomes too deeply involved to remain passive. And that involvement raises a question that cannot be ignored. If the vacuum's behavior changes with energy, then stability itself may be a low-energy illusion, one that holds only because you have not yet pushed reality hard enough to see what it does next. If the vacuum has internal dynamics, then space is not a container. It is a process, and processes can fail. The idea of space as a container is deeply ingrained. It feels natural because it matches everyday experience. Objects occupy space, events occur in space. Space itself appears indifferent, unchanged by what passes through it. This intuition survives because, at human scales, space behaves well enough to support it. Physics no longer agrees. Once the vacuum is understood as a system with energy, pressure, and structure, space stops being a neutral backdrop. It becomes something that is continually being maintained, a state that persists because conditions allow it to persist. A process unfolding moment by moment. Processes are different from containers. Containers endure by definition. A box remains a box unless something destroys it. A process endures only as long as it continues to run correctly. It depends on balance, regulation, and constraint. Remove those, and the process changes or stops. The vacuum looks increasingly like the second kind. Its apparent stillness masks constant activity. Fields fluctuate, parameters run, corrections accumulate. Stability is enforced dynamically rather than guaranteed geometrically. Space does not exist once and for all. It is continuously reasserted by the configuration of underlying fields. This reframes what it means for space to exist at all. You are not embedded in a static expanse. You are embedded in an ongoing solution to a set of equations. That solution happens to be uniform, persistent, and hospitable to complexity. But nothing in the mathematics demands that it remain so indefinitely. When space is a process, change becomes intrinsic rather than exceptional. The laws you experience are not imposed on space from outside. They emerge from the vacuum's current configuration. If that configuration shifts, the laws shift with it. What you call causality, locality, and identity depend on the vacuum behaving in a particular way. This dependence is easy to ignore because the process is stable on observable timescales. But stability is not the same as immutability. A flame maintains its shape and brightness for long periods, yet it exists only because fuel continues to flow and conditions remain within narrow bounds. Remove those conditions, and the flame does not break. It vanishes. The vacuum may be similar. If its internal dynamics require continual balance, then its persistence is contingent. Fields must remain aligned. Energy landscapes must retain their shape. Corrections from higher scales must not overwhelm stabilizing effects. None of this is automatic. When space stops being passive, the notion of failure becomes meaningful. Not failure in the sense of collapse or explosion, but failure in the sense of transition. The process no longer produces the same output. The system moves to a different configuration. From the inside, such a change would not resemble malfunction. There would be no broken geometry, no distorted distances, no warning signs. The process would simply stop producing the space you recognize and begin producing something else. This is difficult to accept because it undermines the idea of space as a fixed arena. It suggests that existence itself depends on ongoing conditions rather than foundational certainty. You are used to thinking that matter depends on space, that particles need somewhere to be. This picture reverses the dependency. Matter depends on the vacuum structure. Space is not what makes matter possible. Space is what emerges when the vacuum's process holds. And processes, unlike containers, are sensitive to thresholds. Push a process beyond its tolerances, and it does not degrade gracefully. It changes regime. It becomes something else. The rules that once applied cease to be relevant. This is why the internal dynamics of the vacuum matter so deeply. They imply that the stability of space is an active achievement rather than a default state. That the universe is not resting on an immutable foundation, but balancing within a viable configuration. When space is passive, failure must come from outside. When space is a process, failure can arise from within. The unsettling implication is not that space will fail. It is that the question makes sense at all. Once you accept that space has dynamics, you must accept that those dynamics have limits. And once limits exist, permanence becomes an assumption rather than a law. Space continues to exist because the process continues to work. Physics does not promise that it always will. Some vacuum phenomena blur the line between cause and effect. Fluctuations appear correlated across space-like separations, not signaling, not communication, but not fully independent either. Causality feels fundamental because your experience depends on it. Causes precede effects. Events unfold in sequence. Nothing influences something else faster than light. These assumptions are so deeply embedded in how you think that they feel synonymous with reality itself. Physics complicates them. In quantum field theory, the vacuum is not a collection of isolated points behaving independently. It is a single, extended system. Fields span all of space at once. Their fluctuations are not local accidents. They are manifestations of global constraints. This becomes visible when you examine correlations. Two regions of space, separated so that no signal could travel between them without violating relativity, can still exhibit correlated vacuum behavior. Measurements performed here subtly constrain what can occur there, not through communication, not through influence traveling through space, but through shared structure. This does not violate causality in the technical sense. No information is transmitted. No usable signal is sent. Relativity remains intact. And yet, the intuitive picture of independent regions linked only by causal chains begins to erode. The vacuum behaves less like a collection of independent locations and more like a single, coherent entity. You can think of it as a tension spread across space. When one part fluctuates, it does so within limits defined by the whole. Those limits create correlations that are not causal in the classical sense, but not random either. This is deeply unsettling because it undermines the idea that causes are always local. In classical thinking, to influence something, you must touch it, push it, or send something toward it. In the vacuum, influence is replaced by constraint. Events are shaped not only by what happened nearby in the past, but by what is allowed globally in the present. Causality still exists, but it is no longer the whole story. These correlations become especially important at high energies and short distances, where vacuum fluctuations dominate behavior. In these regimes, cause and effect blur into statistical structure. Outcomes are not traced to single initiating events, but to the interplay of constraints imposed by the fields themselves. From your perspective, this feels like causality under pressure. The rules still apply, but they no longer feel absolute. They are enforced statistically rather than deterministically. The vacuum does not choose outcomes, it restricts them. This has profound implications. If vacuum fluctuations are correlated across space-like separations, then the vacuum is not merely a background in which causal processes unfold. It participates in shaping which processes are possible in the first place. The order of events you experience may depend less on local chains of cause and more on global consistency. This does not mean the universe is a causal. It means causality is not as fundamental as it feels. It may be an emergent feature of a deeper structure that prioritizes coherence over sequence. At human scales, this distinction disappears. Correlations wash out. Local causes dominate. The world feels solid and predictable. But at the level where the vacuum's dynamics matter, that comfort fades. The vacuum enforces rules that do not map neatly onto cause and effect. It allows correlations without signals, relationships without communication, order without direction. This is not philosophical speculation. It is built into the mathematics that correctly predicts experimental outcomes. Attempts to restore classical causality at this level fail. The data refuses to cooperate. What makes this especially troubling is how it interacts with the idea of vacuum stability. If the vacuum is a globally constrained system, then its stability is also global. A transition is not triggered by a local cause in the usual sense. It emerges from the structure of possibility itself. The system changes because the configuration allows it, not because something pushes it. This reframes how failure would occur. You would not trace it to an initiating event. There would be no cause you could point to. The transition would be the result of constraints resolving differently, of the vacuum selecting a new configuration consistent with its rules. Causality would not be violated, it would be bypassed. The more deeply physics probes the vacuum, the clearer this becomes. Cause and effect are not discarded, but they are demoted. They are no longer the foundation of reality, but one of its approximations. Under pressure, causality bends, and the vacuum is where that pressure is highest. Physics is comfortable with particles interacting. It is less comfortable with emptiness doing the same. The equations allow it. Intuition does not. For most of scientific history, interaction implied presence. Two objects influence one another because something connects them, a force carrier, a collision, a transfer of energy. Even when fields replaced particles as mediators, there was still something acting. Something identifiable, something that could be pointed to as the cause. The vacuum disrupts this logic. When empty space produces measurable effects, when it exerts pressure, alters forces, shifts energy levels, it forces physics to confront an uncomfortable category error. The thing doing the interacting is not a thing at all. There is no object to isolate, no substance to extract, no entity that persists independently. And yet the interaction happens. The equations do not hesitate here. They describe vacuum contributions with precision. They predict their influence accurately. They treat emptiness as an active component of every calculation. From a mathematical standpoint, there is no problem. The problem exists in interpretation. You are used to thinking that if something acts, it must exist in the same way other things exist. It must have location, duration, identity. The vacuum violates all three. Its effects are distributed, transient, and inseparable from the fields that define space itself. This forces a revision of what interaction means. The vacuum does not interact by exchanging something. It interacts by constraining what is allowed. Its influence is not additive, but structural. It shapes outcomes not by acting on particles directly, but by defining the context in which particles can act at all. This is why the vacuum's behavior feels unsettling. It does not fit into familiar categories. It is not an object, not a medium, not a force in the classical sense. And yet, ignoring it produces wrong answers. Physics is comfortable with abstraction, but even abstraction prefers entities with clear roles. The vacuum resists that clarity. It is both background and participant, both absence and influence, both nothing and something. This tension shows up repeatedly in theoretical work. Calculations involving vacuum energy often produce infinities that must be carefully managed. Contributions that seem unphysical cancel only after delicate balancing. The theory works, but only if you treat emptiness with the same seriousness as matter. That seriousness comes at a conceptual cost. Once nothing can act like something, the boundary between existence and non-existence becomes blurred. You are no longer dealing with a universe composed of entities moving through an empty stage. You are dealing with a universe whose stage has agency. This has implications far beyond particle physics. If emptiness can influence outcomes, then absence is no longer neutral. The lack of matter does not imply the lack of effect. Regions you would once have ignored now demand attention. The vacuum becomes a source of structure rather than a lack of it. This challenges a deeply held intuition that removing things simplifies systems. In the quantum vacuum, removal reveals complexity. Strip away particles, and what remains is not simplicity, but a network of constraints and fluctuations that were previously masked. The discomfort comes from the fact that intuition has no way to accommodate this. Human experience offers no analogy for nothing behaving like something. Every interaction you know involves entities with persistence. The vacuum has none. And yet, physics insists. The equations do not treat vacuum effects as optional. They are not corrections added for completeness. They are central. Remove them, and predictions collapse. Keep them, and the universe behaves exactly as observed. This leaves you with a choice. Either reject intuition or reject accuracy. Physics has chosen accuracy. Once that choice is made, a deeper problem emerges. If emptiness can act, then it can also change. And if it can change, then its influence is not fixed. The behavior you attribute to nothing today may not be the behavior it exhibits under different conditions. This is not speculation. The vacuum's contributions already depend on energy scale, geometry, and boundary conditions. Its behavior is context-sensitive. It is responsive. Responsiveness implies variability. The problem, then, is not merely that nothing acts like something. It is that the something it acts like is not guaranteed to remain the same. When physics accepts that emptiness participates in interaction, it accepts that the foundation of interaction is not material. It is structural, and structures can reorganize. The equations allow this. Intuition resists it, but intuition does not determine how reality behaves. The vacuum does. Matter occupies almost none of the universe's volume. The vacuum dominates everything you experience. If it is unstable, nothing else matters. It is easy to forget how little of reality is made of things. Planets, stars, bodies, walls. All of them feel solid, persistent, central. But they are statistical outliers. Almost all of the universe is empty space, not metaphorically empty, literally devoid of matter. And yet, that emptiness is not neutral. Every object you recognize is embedded within the vacuum. Every force you rely on propagates through it. Every particle you are made of is an excitation of fields that exist because the vacuum has the structure it does. Matter is rare. The vacuum is ubiquitous. This reverses an intuitive hierarchy. You are accustomed to thinking that matter defines reality and space merely hosts it. Physics suggests the opposite. Matter is a localized disturbance. The vacuum is the dominant entity, the continuous substrate that determines what disturbances are possible in the first place. If this substrate were inert, its dominance would not matter. But it is not inert. It has energy. It fluctuates. It enforces constraints. It defines masses, charges, and interaction strengths. Remove the vacuum's structure, and matter does not merely disperse. It ceases to be defined. This makes the stability of the vacuum more important than the stability of anything within it. Stars can explode. Galaxies can collide. Even space-time itself can expand or curve dramatically without undermining the existence of physical law. All of these events occur within a vacuum whose structure remains intact. They are dramatic, but they are secondary. If the vacuum were to change, there would be no secondary effects. There would be no matter left to experience them. The unsettling implication is that the persistence of everything you know depends on the continued dominance of a single configuration of empty space, not on the arrangement of particles, not on the balance of forces, on the vacuum itself remaining what it is. This dependence is rarely felt because the vacuum is uniform. It does not announce its presence. It does not vary perceptibly from place to place. Its dominance is invisible because it is absolute. But invisibility does not imply insignificance. The fact that matter occupies so little volume means that almost every interaction you observe is mediated by the vacuum. Forces propagate through it. Fields exist within it. Time evolution unfolds according to rules it encodes. You are not interacting with matter directly most of the time. You are interacting with the vacuum's response to matter. This makes the vacuum less like a background and more like a framework. It does not merely allow interactions. It shapes them. It limits them. It makes some possible and others forbidden. If that framework were unstable, the consequences would not scale with the amount of matter involved. They would scale with the totality of space itself. A local change in the vacuum would not remain local. It would redefine the conditions everywhere it reached. This is why vacuum instability is fundamentally different from any other kind of risk. It does not threaten objects. It threatens the category of objects. You can imagine a universe without stars, without planets, without life. You cannot imagine a universe without a vacuum state, because the vacuum state is what makes imagination physical. The dominance of the vacuum also means that its properties determine what counts as energy, mass, and interaction. These are not intrinsic features of matter. They are relational features defined by how fields behave in the vacuum. Change the vacuum, and these concepts lose their meaning. This reframes the question of stability. You are not asking whether the universe can survive disturbances. You are asking whether the definition of survival is fixed, whether the conditions that allow continuity are enforced or accidental. The vacuum dominates because it is everywhere, because nothing escapes it, because nothing you experience is outside it. Its stability is not one factor among many. It is the factor that makes all others relevant. If it is unstable, nothing else matters, not because everything would be destroyed, but because destruction would no longer be a coherent concept. The most unsettling realization is not that the vacuum might change. It is that everything you care about exists only because it has not. As the universe expands, fields evolve, energy landscapes change. Stability is not preserved automatically over cosmic time. Expansion feels gentle when you think about it. Galaxies drifting apart. Distances slowly stretching, nothing tearing, nothing collapsing. On human timescales, cosmic expansion is imperceptible, almost philosophical rather than physical. But expansion is not passive. When space expands, it does not simply create more room. It alters the conditions under which fields exist. The vacuum is not exempt from this. Its structure is defined by fields whose behavior depends on scale, energy density, and curvature. As the universe grows, those parameters shift. The vacuum is carried along with the expansion, but it is not frozen in place. In the early universe, energy densities were enormous. Fields interacted intensely. The vacuum occupied a very different regime. As expansion diluted energy, fields relaxed into new configurations. Phase transitions occurred, symmetries broke, forces differentiated. What you now experience as stable laws emerged gradually as the universe cooled and stretched. This history matters because it reveals something crucial. The vacuum you inhabit is not timeless. It is the result of evolution. Expansion does not merely preserve the vacuum state. It reshapes the energy landscape in which that state exists. Valleys flatten or deepen. Barriers shift. What was once stable may become metastable. What was once inaccessible may move within reach. Stability, in this context, is conditional on cosmic conditions. As the universe expands further, average energy densities continue to decrease. That changes how quantum corrections contribute to the vacuum's effective potential. It changes how fields sample their possible configurations. It changes the statistical balance that suppresses large fluctuations. None of this implies inevitable decay, but it removes a comforting assumption that time works in favor of stability. In many systems, aging leads to relaxation. High-energy excitations die out. Systems settle into deeper minima. Expansion might seem like that kind of process. The universe cools, things calm down. But cooling can also expose instability. As conditions change, a state that was once protected by high-energy effects may lose that protection. Barriers that once prevented transition can thin. tunneling probabilities can change, not dramatically, but meaningfully. This is not speculative alarmism. It is standard behavior in dynamical systems. Stability is always evaluated relative to conditions. Change the conditions, and stability must be reassessed. The universe does not expand into nothing. Expansion changes the vacuum itself by altering the scale at which its properties are defined. The running of constants continues. Contributions from different energy scales shift in importance. The balance that holds the vacuum in place today is not guaranteed to hold indefinitely. What makes this unsettling is the timescale. Cosmic expansion operates over billions of years. That feels slow, almost irrelevant. But vacuum decay probabilities also operate over immense timescales. What matters is not speed, but direction. Expansion is not static. It is monotonic. Conditions continue to drift. There is no final equilibrium state guaranteed by expansion alone. In fact, expansion can make certain transitions more likely by reducing stabilizing effects. The vacuum may become more sensitive to fluctuations as the universe thins out. Not because it weakens, but because the context that once constrained it evolves. The false comfort comes from assuming that what has lasted will continue to last. Expansion undermines that logic. It ensures that the environment in which stability is evaluated is never fixed. This is especially troubling when combined with metastability. A metastable vacuum can persist indefinitely under constant conditions. Under changing conditions, its expected lifetime becomes a moving target. You cannot assume that time is neutral. Expansion means the universe is not merely waiting. It is changing the terms under which waiting makes sense. The vacuum you experience today is embedded in a universe that is still unfolding. Its future behavior is not determined solely by its present configuration, but by how that configuration interacts with ongoing expansion. Stability, then, is not a static property. It is a dynamic one, maintained moment by moment as conditions evolve. Expansion does not guarantee failure, but it ensures that stability must continually be re-earned, and physics does not promise that it always will be. Early universe inflation may have locked the vacuum into its current state, or it may have left it precariously suspended. The evidence does not decide between these options. Inflation is often described as a solution to problems. It smooths the universe. It explains large-scale uniformity. It accounts for the absence of obvious defects. In that sense, it feels stabilizing, an early act that set the universe on a calm, predictable path. But inflation is also a violent process. For a brief interval after the universe began, space expanded exponentially. Distances doubled again and again in fractions of a second. Energy densities were extreme. Fields were displaced far from equilibrium. Whatever the vacuum was during this period, it was not the quiet configuration you experience now. Inflation did not merely stretch space. It reshaped the vacuum's energy landscape. Fields were pushed up and over barriers. Quantum fluctuations were magnified to cosmic scales. Regions that were once microscopically close became permanently separated. Whatever state the vacuum settled into afterward was not chosen gently. It was selected under conditions of extraordinary stress. This creates an ambiguity that cannot be resolved by observation alone. On one hand, inflation could have stabilized the vacuum. By driving fields into a deep minimum, it may have locked the universe into a robust configuration. One that persists because inflation effectively reset the system into a safe basin from which escape is unlikely. On the other hand, inflation could have done the opposite. It may have frozen the vacuum into a configuration that was never meant to last. By rapidly expanding space, inflation could have suppressed transitions that would otherwise have occurred. Barriers that should have been crossed were made effectively infinite by sudden expansion. The vacuum was not stabilized, it was stranded. Both possibilities are consistent with what you observe: the uniformity of the cosmic microwave background, the distribution of large-scale structure, the absence of catastrophic decay so far. None of these distinguish between a vacuum that is deeply stable and one that is merely long-lived. Inflation leaves a memory in the universe, but it is a blurred one. The fluctuations it amplified are visible today as temperature variations in the cosmic background. But the deeper question, whether inflation settled the vacuum into a true minimum or trapped it in a metastable state, remains unanswered. The signatures overlap. The data does not discriminate. This uncertainty matters because it shifts how you interpret the present. If inflation stabilized the vacuum, then its current configuration is reinforced by history. Its persistence is not accidental, but the outcome of a process that actively selected for stability. The universe would be anchored by its earliest moments. If inflation stranded the vacuum, then history offers no such reassurance. The vacuum persists not because it is optimal, but because expansion prevented transition. In that case, the universe you inhabit is the residue of a temporary suspension. The difference is subtle but profound. One picture frames stability as earned, the other frames it as deferred. What makes this particularly unsettling is that inflation was not a gentle tuning process. It was chaotic at small scales. Quantum fluctuations during inflation determined which regions ended up in which states. Different patches of the universe may have sampled different vacuum configurations entirely. Some may have decayed, some may have stabilized, some may never have formed complex structure at all. You inhabit one region that survived. That fact alone does not tell you why. Inflation complicates the question of vacuum stability because it introduces selection without guarantee. The universe you see is filtered by survival, not by necessity. The vacuum state you experience is one that endured inflation and subsequent expansion, not necessarily one that is fundamentally protected. This reframes the comfort of longevity. The vacuum has lasted for billions of years. Inflation occurred even earlier, but duration does not imply security. It implies compatibility with history. A metastable state can pass through inflation intact and still be vulnerable later. The memory inflation leaves behind is incomplete. It tells you that the vacuum survived extreme conditions. It does not tell you that it cannot fail under evolving ones. And because inflation erased information about what came before, there is no deeper record to consult. The earliest moments that could have revealed the vacuum's true nature are hidden behind expansion. You are left with a universe that looks stable, feels stable, behaves stably, and offers no explanation for why. Inflation may have protected the vacuum, or it may have postponed its reckoning. Physics at present cannot tell you which, and that uncertainty is not peripheral. It sits at the foundation of everything that followed. If decay is inevitable but slow, then existence is temporary by design, not because of entropy, but because of structure. Entropy describes how systems degrade, how order gives way to disorder, how energy spreads out and becomes less useful over time. It explains why stars burn out, why heat flows one way, why complexity eventually dissolves. Entropy is familiar. It feels like aging. Vacuum decay is not that. If the vacuum is metastable, then the universe does not end because it runs out of usable energy. It ends because the configuration that makes energy, matter, and time meaningful ceases to apply. The failure is not gradual, it is structural. This distinction matters because it changes what existence means. In an entropy-driven universe, existence is guaranteed at the beginning and exhausted at the end. There is a clear arrow: formation, evolution, decay. In a metastable universe, existence is provisional at every moment. It is not promised at the start. It is granted moment by moment as long as the structure holds. The universe does not age toward its end. It waits. A metastable vacuum can persist for inconceivably long periods, long enough for galaxies to form, stars to live and die, civilizations to rise, ask questions, and disappear. From the inside, this persistence feels indistinguishable from permanence. From the outside, it is delay. The unsettling implication is that nothing you experience requires the universe to exist indefinitely. There is no law that demands continuation. There is only probability favoring persistence over short timescales. Existence in this view is not a default state. It is a metastable outcome. This reframes cosmic history. The early universe did not simply begin and then unfold. It settled into a configuration that allowed unfolding to occur. That configuration could, in principle, have been different, or could change. The fact that it has not changed yet is not evidence that it cannot. It is evidence that it has not. This is difficult to accept because it strips existence of inevitability. You are accustomed to thinking that something must exist, that nothingness requires explanation. Metastability reverses that intuition. It suggests that existence itself is what requires explanation, and that the explanation may be historical rather than necessary. The universe exists because it entered a configuration that persists, not because it must. This is why delay is the correct word. Delay implies intention without agency, a pause enforced by structure, a system that remains in a state not because it is final, but because transition is suppressed. Suppression is not prevention. If decay is inevitable but slow, then the universe is not progressing toward an end. It is occupying time before a transition. The arrow of time you experience is not leading toward decay of structure, but toward a moment when structure itself becomes irrelevant. This does not make existence meaningless. It makes it conditional. Every moment you experience depends on the vacuum continuing to behave as it has. Every law you rely on persists because the underlying configuration has not yet changed. There is no deeper guarantee beneath that. This is not fatalism. It is precision. Physics does not claim that the universe will decay tomorrow. It claims that if metastability is real, then the universe exists on borrowed time in the strictest sense, not borrowed from the future, but borrowed from possibility. Existence is allowed to continue because the structure permits it. Structure can change. The unsettling part is not that the universe might end. It is that the reason it exists at all may be that it has not yet stopped. Not because of entropy wearing it down, but because the configuration that defines reality has not yet been replaced. A universe that exists by delay does not announce its deadline. It simply continues until it does not. The danger is not imminent. That is not the point. The point is that stability is not fundamental. It is conditional. Discussions of vacuum instability often trigger an instinctive reaction, alarm, dismissal, or both. If the universe could end this way, why has it not already happened? If the probability is so small, why worry at all? These responses miss what physics is actually saying. This is not a prediction of catastrophe. It is a statement about foundations. Physics is not warning you that the universe is about to fail. It is telling you that the reason it has not failed is not written into the deepest laws we know. Stability is not a guaranteed feature of reality. It is an outcome, one that depends on specific parameters, historical conditions, and probabilistic suppression. That distinction matters. Doomsday implies a clock, a countdown, a deadline toward which events are moving. Vacuum instability offers none of that. There is no timeline, no trajectory, no accumulating risk in the everyday sense. The probability does not grow louder with time. It simply exists. This is why the idea resists emotional framing. There is nothing to prepare for, nothing to mitigate, nothing to avoid. The concept does not fit into narratives of threat or survival. Instead, it forces a quieter realization. The laws of physics you experience do not insist on their own permanence. They hold because the vacuum configuration that supports them holds. That configuration is not demanded by logic. It is allowed by structure. Stability, then, is not a principle. It is a circumstance. This reframes how you think about what is fundamental. You are used to ranking laws by depth. Conservation laws feel deeper than chemistry, which feels deeper than biology. But vacuum stability sits beneath even those distinctions. If the vacuum changes, the hierarchy itself dissolves. What makes this unsettling is not fear of ending, but loss of necessity. The universe feels inevitable because it is consistent, because it obeys rules, because those rules have never visibly failed. Physics now suggests that this consistency may be contingent, that the rules persist not because they must, but because nothing has yet displaced them. This does not cheapen existence, it clarifies it. You are not living in a universe protected by absolutes. You are living in one maintained by balance. That balance has held across cosmic time, but holding is not the same as being required to hold. The mistake is to treat this insight as apocalyptic. It is not a story about the future. It is a statement about the present, about what kind of thing reality is. A universe with conditional stability is not fragile in the everyday sense. It does not crack under pressure. It does not drift toward collapse. It can persist longer than imagination allows, but its persistence is not enforced by necessity. Physics has encountered this pattern before. Atoms were once thought indivisible. Stability was assumed. Later, deeper structure revealed conditions under which atoms could decay, not catastrophically, not suddenly everywhere, but conditionally. What seemed fundamental became provisional. Vacuum stability appears to follow the same pattern. This is why the idea matters even if decay never occurs. It tells you that the universe you experience is not the only possible one consistent with the laws, that what exists does so because it is allowed, not because it is demanded. Doomsday physics predicts an outcome. This predicts a dependence. It tells you that reality is not anchored by permanence, but by configuration. That existence is not guaranteed by law, but permitted by structure. That the deepest question is not how the universe will end, but why it exists in this form at all. The danger is not imminent because danger is the wrong concept. The insight is unsettling because it removes a quiet assumption you did not know you were making, that stability is fundamental, that the universe must be this way, that reality rests on something unchangeable. Physics suggests otherwise. Stability is not the ground, it is the arrangement. And arrangements, no matter how long they last, are not the same as laws. You are not standing in space. You are embedded in overlapping quantum fields that define mass, charge, and time. Their arrangement is not guaranteed. The language you use to describe reality hides this fact. You say objects exist in space as if space were an empty container and matter were the content placed inside it. That picture is intuitive, but it is wrong at the deepest level physics can reach. There is no empty stage beneath you. What exists everywhere are fields. Continuous entities that do not occupy space so much as constitute it. The electron field, the quark fields, the electromagnetic field, the Higgs field, each one extends through all of reality. What you perceive as particles are localized excitations of these fields. What you perceive as empty space is simply a region where those excitations are absent, not where the fields themselves vanish. You are not standing on anything. You are immersed in something. Your mass exists because the Higgs field has a particular value here rather than another. Your atoms hold together because gauge fields behave in a specific way. Time progresses because the vacuum configuration allows stable evolution rather than immediate collapse or runaway growth. Every aspect of your existence is conditional on this arrangement. This is easy to forget because the arrangement is uniform. The fields do not flicker perceptibly. Their values do not change from room to room. The consistency creates the illusion of inevitability. It feels as though space simply exists, and you happen to be in it. In reality, you exist because the fields remain arranged as they are. Field configurations are not abstract bookkeeping devices. They are physical states with energy, structure, and possible alternatives. Different configurations correspond to different vacua. Different vacua correspond to different realities, not different locations, but different rules. Change the configuration, and mass may not exist, or charge may behave differently, or stable matter may be impossible. There is nothing sacred about the particular arrangement you inhabit except that it works. This is where the discomfort lies. If you lived inside a solid structure, you could imagine it breaking. If you lived inside a machine, you could imagine it failing. Living inside a field configuration feels different because there is nothing to point to. No walls, no mechanisms, no visible supports. And yet, the support is there. The configuration of fields is doing continuous work. It suppresses certain fluctuations. It enforces symmetries. It stabilizes interactions. It prevents the vacuum from exploring other arrangements that are mathematically allowed, but physically incompatible with complex structure. You experience this as normality. Physics experiences it as constraint. The unsettling realization is that nothing about this arrangement is logically necessary. The equations allow many configurations. Some would produce radically different universes. Some would collapse immediately. Some would never permit observers to form. The one you inhabit is simply one that persists long enough to be noticed. This does not mean it was chosen. It means it survived. Living inside a field configuration means that existence is contextual. It depends on the continued validity of relationships that are not enforced by absolute law. They are enforced by energy landscapes, barriers, and probabilities. This reframes identity. You are not a collection of particles moving through empty space. You are a pattern sustained by fields behaving in a particular way. Your body is a stable configuration within a larger stable configuration. Your thoughts depend on chemistry, which depends on electromagnetism, which depends on the vacuum structure. There is no layer beneath that which guarantees permanence. The idea that their arrangement is not guaranteed is not meant to provoke fear. It is meant to clarify dependence, to show that what feels foundational is in fact contingent, that what feels like a given is the outcome of balance. Physics does not claim that the configuration will change. It claims that nothing forces it to remain unchanged. This is a subtle but profound shift. Instead of asking what exists, you must ask under what conditions existence is possible. Instead of assuming space as a given, you must see it as a state, one that can, in principle, be replaced. You live inside that state. Everything you know is defined by it, and its persistence is a fact of history, not a guarantee of logic. That is what it means to live inside a field configuration. Not to stand on reality, but to be continuously upheld by it. The laws you rely on may not be eternal truths. They may be the current configuration of a deeper system, a solution, not a necessity. It is natural to treat physical laws as timeless. Gravity pulls, light propagates, charge is conserved. These rules feel permanent because they have never failed within observation. They feel less like descriptions and more like obligations imposed on reality itself. Physics no longer makes that claim. At the deepest levels, laws increasingly resemble outcomes rather than axioms. They emerge from how fields are arranged, how symmetries are broken, how energy landscapes are shaped. Change the arrangement, and the laws change with it. Not because the universe rebels, but because the rules were never fundamental to begin with. This is difficult to accept because it inverts how explanation usually works. You want laws to explain structure. Instead, structure explains laws. The vacuum configuration you inhabit selects which interactions exist, which particles are stable, which processes are allowed. Conservation laws arise because symmetries exist. Symmetries exist because the vacuum has a particular structure. None of this is logically required. It is contingent. This means the laws you rely on are not written into the fabric of existence. They are written into the current state of that fabric. In physics, a solution is a state that satisfies equations under given conditions. Solutions can be stable or unstable. They can be unique or one among many. They persist not because they must, but because nothing forces them to change. The universe you experience may be exactly that, a long-lived solution to deeper equations. Those deeper equations do not specify electrons, light, or time as you know them. They specify relationships between fields, constraints on energy, and allowable configurations. What emerges depends on which solution is realized. This reframes reality as provisional, not in the sense that it is flimsy or unreliable, but in the sense that it is not inevitable. There are other solutions the equations permit, other ways the vacuum could configure itself. Most would not resemble anything you recognize. The unsettling implication is not that the laws will change tomorrow. It is that nothing in the structure of physics guarantees that the laws you know are the only ones possible, or that they are the final ones. This does not mean physics is incomplete in a trivial sense. It means physics is honest about what it describes. It describes the behavior of a particular solution, not the necessity of that solution. From this perspective, asking why the laws are what they are becomes a different kind of question. It is no longer answered by deeper law alone. It may require historical explanation, or probabilistic reasoning, or acceptance that some features are simply outcomes rather than reasons. Reality, then, is not the inevitable expression of logic. It is a state that works. This idea is deeply unsettling because it removes the sense that existence is grounded in necessity. It suggests that what exists does so because it satisfies conditions, not because it is required by reason. Your universe is coherent because its configuration is coherent. It supports structure because its vacuum allows structure. It persists because the solution remains valid. None of that implies permanence. Temporary does not mean brief. In physics, temporary can span trillions of years. But temporary does mean contingent. It means dependent on conditions that could, in principle, be different. Seeing reality as a temporary solution does not reduce its significance. It changes its interpretation. Existence becomes something that happens, not something that must happen. Laws become properties of a state, not dictates imposed from outside. This view aligns uncomfortably well with what modern physics reveals. Parameters appear tuned. Stability appears conditional. Symmetry appears broken rather than absolute. Everywhere you look, necessity gives way to configuration. The universe behaves less like a theorem and more like a result, and results can change when assumptions change. This does not imply that reality is arbitrary. The deeper equations still constrain what is possible. Not every solution is allowed. Not every configuration is viable. But among those that are allowed, only some persist long enough to be experienced. You live inside one of those. Reality, as you know it, may be a temporary answer to a deeper question. One that has held for billions of years. One that supports complexity, thought, and reflection. But one that is not guaranteed by logic alone. A solution is something that works. A necessity is something that cannot be otherwise. Physics increasingly suggests that reality belongs to the first category, not the second. And once that distinction is clear, permanence stops being an assumption. It becomes an open question. The vacuum does not announce its intentions. It behaves consistently until it doesn't. Silence is not reassurance. There is something deeply misleading about consistency. When a system behaves the same way again and again, you begin to trust it. Patterns repeat. Expectations form. The absence of surprise feels like stability. Over time, silence becomes synonymous with safety. Physics warns against this assumption. The vacuum has behaved consistently for as long as the universe has been observed. Its fields maintain their values. Its structure supports matter, energy, and time without visible fluctuation. Every experiment conducted within it confirms the same rules. Every observation reinforces the same framework. And yet, none of this guarantees permanence. The silence of the vacuum is not evidence of intention. It is not a promise. It is simply the absence of transition so far. A metastable system does not announce that it is metastable. It behaves exactly like a stable one until the moment it changes. This is why the vacuum's silence is unsettling rather than comforting. In systems you understand, silence often indicates equilibrium. A quiet machine is running smoothly. A calm sea is stable. But in those cases, silence is maintained by feedback, by forces that resist deviation, by mechanisms that actively suppress change. The vacuum offers no visible feedback. Its silence does not come from correction. It comes from balance. And balance, as physics has shown repeatedly, can persist without protection. This creates a tension between observation and inference. Everything you measure confirms stability. Nothing you measure proves necessity. The vacuum does not behave suspiciously. It behaves perfectly normally, and that is the problem. If the vacuum were unstable in an obvious way, physics would have noticed. If it drifted, fluctuated wildly, or showed signs of weakening, the question would be different. But it does none of these things. It supports reality flawlessly. The possibility of failure arises not from behavior, but from structure. The equations that describe the vacuum allow multiple configurations. Some are lower in energy than the one you inhabit. Transitions between configurations are permitted in principle. Suppressed? Yes. Rare? Yes. But allowed. The vacuum's silence does not contradict this. It is consistent with it. A metastable state does not whisper warnings. It does not degrade. It does not hesitate. It simply persists until it does not. From the inside, there is no difference between a state that will last forever and one that will last 1 trillion years. This is why reassurance is unavailable. No measurement can confirm absolute stability. No observation can rule out eventual transition. The silence of the vacuum is compatible with both outcomes. It tells you nothing about what lies beyond the current configuration. This is deeply uncomfortable because it removes a familiar anchor. You are used to thinking that stability reveals itself through behavior, that what works reliably is safe. Physics does not support that inference at this level. The vacuum's silence is not a signal of intent. It is a condition of its role. It does not announce because there is nothing to announce. The transition, if it occurs, is not prepared. It is not anticipated. It is not preceded. It simply replaces the context in which anticipation is meaningful. This reframes how you interpret quiet. Quiet does not mean inert. Quiet does not mean resolved. Quiet does not mean permanent. It means unchanged so far. The unease comes from realizing that the vacuum's silence cannot be interrogated. You cannot stress test it into revealing its future. You cannot probe it into confessing stability or instability. Every test you perform is conducted within the very structure whose future you are trying to assess. The vacuum answers questions about how it behaves now. It does not answer questions about how long it will continue to behave that way. This is not a failure of physics. It is a boundary of what can be known from within a system. A system cannot fully certify its own permanence. The vacuum's silence is unsettling because it offers no resolution. It neither promises continuation nor threatens change. It simply continues, and that continuation, repeated over billions of years, creates the illusion of reassurance. Physics refuses that illusion. It tells you that silence is compatible with stability and metastability alike, that consistency is not proof, that absence of change is not a guarantee of future behavior. The vacuum does not announce its intentions because it has none. It follows its structure, and structure, unlike promise, does not care how long you have been listening. If nothing is unstable, and instability can end everything without warning, then existence is not grounded in permanence. It is grounded in delay. And that leaves one unresolved question hanging beneath all of physics. Not whether the vacuum will fail, but why it has not already done so. This question does not arise from fear. It arises from consistency. Physics has followed its principles to their logical conclusions, and those conclusions do not provide reassurance. They provide structure. And within that structure, delay is the only explanation left standing. The vacuum behaves as if it is stable. It supports particles, fields, and time itself with extraordinary reliability. But the same equations that describe this reliability also permit its failure. There is no contradiction, no paradox, just a quiet asymmetry between what has happened and what must happen. The question, then, is unavoidable. If the vacuum is metastable, why has it persisted for billions of years? If decay is allowed, why has it not occurred? If probability is non-zero, why has it not been realized? Physics does not answer these questions by invoking purpose or protection. It answers them by pointing to suppression, to barriers, to probabilities so small that expectation times dwarf cosmic history. But suppression is not prohibition. Probability is not impossibility. This leaves you with a universe that exists not because it must, but because it has not yet done otherwise. That distinction reshapes how existence itself is understood. Delay is not a mechanism, it is a condition, a state in which transition is allowed but not realized. The vacuum persists because it remains within a configuration that has not been displaced, not because displacement is forbidden, but because it has not yet occurred. This makes the present moment conceptually fragile in a way that does not register emotionally. You do not feel precarious. Reality does not feel thin. The vacuum does not tremble. Everything behaves exactly as it always has. And yet, physics insists that this behavior does not exhaust the possibilities. The question that refuses to settle is not about prediction. It is about explanation. Why this configuration? Why this balance? Why this delay? Some answers gesture toward deeper structure, unknown symmetries, new physics at higher energies, constraints that have not yet been discovered. These possibilities remain open, but they are not confirmed. They are hopes for necessity where only contingency is currently visible. Other answers invoke selection. Perhaps only universes that persist long enough can be observed. Perhaps decay has occurred elsewhere, in regions forever inaccessible. Perhaps this vacuum is simply one that survived long enough to be noticed. These explanations do not eliminate the question. They relocate it. Why this survivor? Why this configuration? Why now? The refusal of the question to settle is not a failure of understanding. It is a sign that understanding has reached its edge. Physics has traced the logic of stability as far as it goes, and it ends not in certainty, but in suspension. Existence appears less like a foundation and more like a condition being continuously met, not actively maintained by an agent, but passively allowed by structure. A state that continues because the conditions for change have not yet been satisfied. This does not trivialize reality. It deepens it. It suggests that what exists does so not because it is inevitable, but because it is possible. That the universe is not the only answer to the equations that define it, but one answer that has not yet been replaced. The unresolved question remains precisely because it cannot be dismissed. It sits beneath every law, every constant, every measurement. It does not ask when the vacuum will fail. That would imply a clock. It asks why persistence has outpaced possibility, why delay has held, why a universe governed by laws that allow transition has not yet transitioned. Physics does not offer reassurance here. It offers honesty. It admits that permanence is not guaranteed, that stability is conditional, and that existence rests on a configuration whose endurance is a fact, not a necessity. The question refuses to settle because there is nothing beneath it to settle on. Only structure, only probability, only delay. And in that delay, everything you know continues. Quietly, consistently, without explanation. For now.